Okay, so let's go for problem 5. Express the statement a Bloomfield student must take at least 60 course hours or at least 45 and write a master's thesis and receive a grade no lower than B in all required courses to receive a master's degree. All right, so there's lots of information going on, but let's dissect this. Okay, so let's take a look at this first part. So all of these statements are, all of these are the requirements to get a master's degree. Okay, so I think we need to come up with some of the predicates. So first, I'm going to call it M, and I'm going to call it M of, sorry, not M, but let's do H for hours. So H of X, and I'm going to define this as a student took X course hours. Okay, so that's my first predicate. And seems like I need to have a 1 for thesis. Doesn't really need a variable, so I'm just going to call it T. And T is that wrote thesis. Alright, and then I need another one. Grade no lower than B in all required courses. So this is a letter grade and all the courses. So it seems like I need 2 variables. So I'm going to come up with G, and I'm going to say this is X comma Y. And I'm going to define this as receive grade X. Oops. In course called Y. Alright, so after I've defined all of this, let's write the statement. Okay, so Bloomfield student must take at least 60 course hours, so that's going to be of 60, or at least 45 and master's thesis. So we know that this is one statement, must take 60 course hours or at least course hours and write a thesis. Okay, so probably I'm going to have to do in parentheses 45 and do thesis. Okay, so all of this is conjoined by another and statement, and receive a grade no lower than B. So I'm going to use the G. Receive a grade is B in this case, in all required courses. So it's going to be G comma Y, and this is for all, so I'm going to do for all courses Y. Okay, this is it. So you can say that this will give them the master's degree, or I guess the order doesn't really matter. You can also say to get a master's degree, which you can put the M at the front, to get a master's degree, and put the right-sided arrow. Okay, so this is going to be the answer for problem 5. Okay. So this is pretty famous proof. It might be good. It might be a good idea if you go over different. If you read over this proof online before taking the test. But I'll go over this proof. The proof that root 2 is irrational. So we're going to prove by contradiction. So in this case, we're going to say root 2 is rational. And if this proof fails, then we have proved that this is not rational, which means root 2 is irrational. Okay. The definition of irrational is that a number can be written in a fraction form. So this gives us the chance to write it as P over Q. And there are many different types of forms that we can take on a P over Q. So for example, 2 over 4, this is the same thing as 6 over 12. This is the same thing as 50 over 100. So because there will be lots of different infinite number of fractions available, I'm going to call it and say, define that I'm only going to take on the most reduced form. So I would have to define where P and Q have no common factors. So this means that for our example here, 1 over 2 is the only fraction that I'm going to take. Okay, now let's square both sides. So that's going to give us 2 equals 2 p squared over q squared. And let me multiply q squared to both sides. So we have 2q squared equals to p squared. This tells us that p squared is an even number because any number times 2 results in an even number. And this also shows that only even squared gives us an even number. So this gives us the fact that p is an even. Okay, if you think about it closely, P is, so let's take a few examples of P must be even. So if P is 2, the smallest even number is 2, it could be, or 0, it's 0. If P is 2, it's 4. If P is 4, it's 16. If P is 6, 36, and so on. And notice how P squared, these are all divisible by 4, or factors of 4. So 0 divided by 4, this is a divisor. 0 can be divided by 4. 4 can be divided by 4. 16 can be divided by 4. 36 can be divided by 4, and so on. So we know that P, this one is something 4k, 4 times some number. Okay, so I'm going to go ahead and write that. 2p squared is something 4k. Divide 2, both sides gives us p squared equals to 2k, which also gives us the fact that p squared, I'm sorry, this should be q's. Right. So 2q squared equals to 4k, this is also q. So this tells us that q squared is even, which gets us the fact that q is even. All right, so if q is even, let me write q as maybe 2m, where m is any number. So essentially we have defined the square root as p over q at the beginning, and we ended up something like p was 2k or 4k, right? I'm sorry, p is even, so I'm just going to do 2k. And also we got to the conclusion that q is also even, so this is 2m. This is a contradiction to where we have said that p and q have no common factors, because it seems like they do have common factors. So therefore, this cannot be true. So this is how we prove by contradiction that square root of 2 cannot be rational, which means that it has to be a irrational number. Okay, so let's go over our last problem. For this, we're going to try to prove that by implication. Okay, so we're going to try to imply that if the first one is true, then second one should be true. That should also imply the third one should be true, getting us to the last one. Okay, so let's first assume that n is even. So n is even, meaning that we can write this as 2 times k, where k is just any integer. And let's try to get to the second one. So n plus 1. So I'm going to add 1 to both sides. So n plus 1 equals 2k plus 1. And as we know, that if we add 1 to an even number, we're always going to result in an odd number. So this is satisfied. So we have just proved that if statement 1 is true, that implies the second statement is true. Okay, so we're going to continue from the second statement where n plus 1, assuming that n plus 1 is an odd number. All right, so third statement tells us that 3n plus 1 is odd. So let's check if that is correct. So 3n, this could be written as n plus n plus n plus 1. And using our second one, which we're assuming to be true, n plus 1 should equal to 2k plus 1. So let me plug that in. So we have 2n plus 2k plus 1. I'm going to take out the 2, n plus k plus 1. So we know any number times 2 is going to result in an even number. And when we add 1 to any even number, that's going to result in an odd. So therefore, this we have just shown that if the second statement is true, this implies that our third statement is also true. All right, so we have come up to this part. We just have to prove the last one. So let's see if 3n is even. I'm going to start off from our previous statement where 3n plus 1 was odd. So I can rewrite that as odd, meaning 2 times any number plus 1. All right, so from here, let's see if we can get to our last part where we have to prove that 3n is even. We subtract 1 from both parts, so we have 3n equals to 2k. So this proves that 3n is even. So therefore, we have used part 3 to get us to imply for part 4 being true. So this whole process, we have shown that if n is integer, then these 4 statements are stating the same thing.